In this lecture, we're going to look at how to solve a discrete system that involves a torsion of a shaft. It's very similar to how we did it for springs and the elongation of bars. So the angle of twist of a constant cross-sectional area cylinder is related to our torque. So our torque is our shear modulus times our polar moment of inertia divided by our length times our twist angle theta. Just as we did for springs and bar, we can make a relationship between the two ends. So if I have a torsion element, I can twist my two ends. I'd have a theta at each end, I'd have a torque at each end, have a theta at each end, and torque. So my torque at end 1 would be equal to Gj over h, and again this is for each element, times my relative angle of displacement. Those are thetas, I know. Just bear with me, they're thetas. Our torque at N2 would still be Gj over h times our relative displacement of our two ends. Or if we were to put this in matrix form, we would simply get that our two torques are equal to Gj over h times 1 minus 1 minus 1, 1, where this is your element level stiffness matrix times our twists at our two ends. So we're going to look at an example. This is example 3.33 in, I believe, the 3rd edition, possibly the 4th edition. Oh no, it's in the 4th edition. It's in the 3rd edition as well, but that's in chapter 4. We have a circular shaft consisting of a 10-inch long, 7/8 inch diameter steel cylinder, which has a 5-inch long, 5/8 inch diameter hole drilled in from end to B. The shaft is attached at both ends to fixed rigid supports, and a 90 foot-pound torque is applied at its midsection. We want to determine the amount of twist at the midsection and the torque exerted on the shaft by each of the components. We're given the modulus as 11.5 times 10 to the 6th. So what do we have? Well, we have two elements, right? We have element 1, we have element 2, broken apart by our torque is applied at point 2, so we have 3 points in our system. And if we look at our free body diagram, it's showing us that we have the torque of element 1 end 2 plus the torque of element 2 end 1 is equal to our applied torque T. And our angles of twist, which they used U here, I'll make those thetas. Our angles of twist at our two ends are 0 since our two ends are fixed. So from our free body diagram, the information that we gathered is we need to add equation 2 of element 1 to equation 1 of element 2. We can also look at this as what's connecting point 1, what's connecting all of our points. So our system of equations is K11, K112, 0 times K121, K122 plus K211, K212, 0, K221, K222. So something we're going to note is that our stiffness matrices are always symmetrical, and if you have elements connected in series, they simply sum along the diagonal. This is going to be times theta 1, theta 2, theta 3, which is equal to T11, T12, T12 is T21, T22. Now, for element 1, G1, J1 over H is 11.5 times 10 to the 6 times pi over 32 times 7/8 to the 4th over 5, which is 132. And then for element 2, is 11.5 times 10 to the 6 times pi over 32 times 7/8 minus 5/8 over 5, which is 97.98 times 10 to the. So then we have our boundary conditions, which are that theta 1 and theta 3 are equal to 0, and that T2, which is equal to T12 plus T21, is equal to our applied torque. So in this case, our condensed equations are only equations 2, which is K122 plus K211 times theta 2 equals our applied torque. So theta 2 is our applied torque divided by K122 plus K211, which equals 90 foot-pounds divided by 230.46 times 10 to the 3 pounds per inch, 12 inches per foot. We get an answer that our angle of twist is 4.6863 times 10 to the minus 3 radians. We always have to go back and determine our unknown reaction forces by solving rows 1 and 3. So we get that T11 is equal to K112 theta 2, which is equal to minus 132.483 times 4.6863 times 10 to the minus 3, which is minus 620.84, and T22 is equal to K221 theta 2, which is equal to minus 97.98 times 10 to the 3 times 4.6863 times 10 to the minus 3, which equals minus 459.16 pound inches, which is minus 38.263 foot-pounds. And the first one was minus 51.737 foot-pounds. In the next video, I'll go over electrical circuits, which is really where learning how to assemble the system based on connectivity comes into play.